Hello everyone, and welcome to this presentation about how to reverse engineer your CAN bus and build an ECU using Elixir. I'm Thibault, and I'm a software engineer, and together with two colleagues we have built Spin42, which is an IT and consultancy and product company. And for about 7 years we've built an open banking aggregator using Elixir. And after so much time in finance, we wanted to explore new opportunities and see how far we could go with Elixir and if it could be a good fit for the automotive use case. So in 2024, we took a sabbatical and we have built the Open Vehicle Control System, which is an Elixir-based dev kit allowing you to upgrade any vehicle. And by upgrade, we mean converting it to an EV, swapping the engine, creating a new infotainment system, and hopefully at some point we hope to allow you to transform your vehicle into an autonomous one. So in our case, we used the 207 diesel Polo, and the first thing we did was to convert it into an EV by putting a Nissan Leaf electric motor in it. I won't go into the details of the mechanical work. There is a lot to say there, but that's not the topic of the day. And today, to show you how to do the reverse engineering in practice, we will just focus on a very simple use case, which is how to make the VW dashboard display the RPM value from the Leaf motor. So that's one of the things you need to do if you want to have a seamless integration between parts from different manufacturers. So you may know it or not, but in all of your cars you have a CAN bus, so that's a controller area network, and that's basically a twisted pair of copper on which all the components of your car are connected and are sending frames. That's a standard protocol used in automotive, but also in planes, trains, even for industrial machines. And the good thing is that you have built-in support in the Linux kernel using libsocket CAN. And then the way to send frames on that bus is standard, but the content of the data, the values that are sent are not at all. And of course, car manufacturers are not providing any kind of documentation. So this is what CAN bus frames are looking like, what it looks like. So you have here a list of frames that are exchanged on the bus of the Polo. You have a list of frames with their IDs, the frequency at which they are emitted, so that it's broadcasted and all the components can receive all the frames. And then you have the raw bytes that you have to make sense of. And so when the color is changing, it means that something happened. So if you pull the handbrake, you will have some bits changing somewhere, and you have to find which frame is linked to what and which value means what. So yeah, the main idea is that you have these frames emitted periodically on the bus. Then the tools that we used, first you need to physically connect to that bus. So we used a simple USB CAN device such that we could hook up with the laptop. And then the screen you've seen before is from Savican. That's an open source GUI that allows you to display the values and also replay frames and so on. And then one tool that is a bit less known is SocketCanD. That's a daemon that allows you to stream a CAN bus over IP. And that's quite useful because then if you put a Raspberry Pi running this in your car, you can work from your desk on your laptop and you can send and receive frames in real time so that you can have smaller cycles. All right, so first thing we need to do is to be able to receive that RPM value, so the rotation per minute from the Leaf motor. And yeah, we chose the Leaf motor because you have kind of a large community of thinkers that already reverse engineered actually the frames on the Nissan Leaf. So we could find some DBC file on the internet. So the DBC file, it's a frame specification file. And in one of these files, while browsing it, we could find the inverter status frame in which you have that 15 bits of output revolution, which is supposed to be a big identity encoded unsigned integer. And then, yeah, to validate this, because that's a community source, we just connect it to the motor, make it run. And then, actually, it seems to be the two full bytes, so the 16 bits. It's big Endian indeed, but it's a signed integer because the motor code can go both ways, so it can go backward too. So that was easy, not that much of reverse engineering. Okay, so we can read it. Now we also have to be able to send the value to the Polo dashboard. And in that case, we made kind of a big mistake because when we got the car, we jumped ahead, removed the engine, all the parts we didn't need it. And then we started thinking about, okay, but how do we reverse engineer that now? So if you want to do this, before doing anything, just go for a drive, you record the whole can, so that you have an example of all the frames. Anyway, so there is not such a big community about the VW Polo, but still we could find someone else that did some research on another Volkswagen of the same generation. So it seems that the frame 280 has the RPM value in the second and third bytes in Little Endian, since he's shifting the bytes. So using that hint, what we did to validate it is that we use the frame sender interface of Savican, where you can define a frame that you want to send, which data at which frequency. It turns out that the dashboard of the Polo is also validating the frequency at which it's emitted, so we had to try a few values for this. And after a few tries, we had that needle moving, so that was already quite a success. But actually on a CAN bus, you often don't send the value as is. It's most of the time it's scaled and sometimes offsetted. So you need to reverse engineer that scaled value. Again, the usual way for that kind of value is to drive the car, you record a picture of the dashboard, and then you match the timestamp of the CAN bus that you have recorded as well, and then you try to match them. In this case, it was not possible again. But actually, that was even simpler, because since we could control the value that was emitted, then we just had to read the approximate value displayed by the needle. Then you put that in a spreadsheet, and then it's quite easy to guess the scaled value. And once you have the two curves that matches, you know that you have the right scale. So yeah, it's a bit tedious, but actually you don't have any encryption, you don't have any anti-reverse engineering methods. So it's just about finding the right bits and then how to interpret them. All right, so now we know how to read the value, we know how to send it. We are missing something in between that will do the conversion. So that's the ECU we are building today, so the vehicle management system. And we put this in between the two buses. We don't mix the components from the Leaf and from the Polo on the same physical CAN bus, because you could have the same ID used by the two manufacturers for different use cases. So we could keep these segregated. And then we will build some code in Elixir that will do the translation and proxy the value in between. So let's do this. Why Elixir? Well, first because we liked it, and also if you may know it, but that's a functional language running on the Beam, which is the Erlang Virtual Machine. And that virtual machine has been designed by Ericsson a long time ago to build telephony switches. And so that's designed to build soft real-time applications. And it's also the CAN use case is quite close to that telephony use case, because you receive bytes, you have to handle them and then forward them to somewhere else. So you can see that the language is really fitting that use case pretty well. And the pattern matching feature that they have built is really nice to parse the frames and extract data in a maintainable and readable way. Concretely, that's all the lines you need to connect to a CAN bus. And sorry. and receive one frame. So you have the first few lines that are about connecting to the socket and binding it. And then you have that socket receive function that will block until a frame comes in on the bus. And then from line 8 to 13, you have that pattern matching where we assign to the ID variable the first 16 bits as an integer encoded in Little Indian. We skip 2 bits, we extract the number of bytes in the data, skip 3 bits again, and then we extract the raw data based on that number we just found. And then if the ID matches, we will extract the RPM value as that big Indian sign integer and then just show it on the console. So it's quite concise, it's quite readable according to me. It's quite different to what we would see in some other languages if you already did that. So you could feel that it's a good match. Still, when you have to receive and send a lot of frames, it can be a bit tedious to do everything manually. So while we were building the Open Vehicle Control System, we also extracted an open source library that will just focus on providing an easy interface to emit and receive frames. So basically, you will define a YAML file in which you define all your CAN buses and all the frames and the signals, so the values in it. And Cantastic will make sure it converts with the right scale, offset, and so on for you. You don't have to think about it. And it will also then spawn one process, so in Elixir, that's a gen server, per network to have a receiving loop, and then it will dispatch the frame to all the processes that subscribe to it. And finally, you will have one emitter process per emitted frame, and it will take care of emitting it at the right frequency and do the conversion of the values. All right, so let's build this using Cantastic then. So on the left, you have the YAML file with that leaf drive CAN network. And then we have a received frame, so for the inverter status one that we found on the DBC file. And we define that rotation per minute as a big Indian integer. And then on the right, we have our simple business logic code that is implemented also as a gen server. So we spawn a process. When it starts, it will subscribe to the inverter status frame, and then Cantastic will send a message to that process every time the frame is received. We extract the RPM value, and then the only thing we have to do is send it to the dashboard process. On the dashboard side, we define just one emitted frame, so the engine status one. We apply the scale that we reverse engineered, so we don't have to think about it in the business logic. And here we will just configure the emitter such that it starts emitting immediately with RPM of 0. And we implement that set rotation per minute function that will just update the emitter with the new value. Of course, VW didn't expect the DSL engine to run backwards, so we use the absolute function call to only send positive values. And the good thing is that this call will be called every 10 milliseconds because that's the frequency of the leaf frame, but the emitter will only send it every 100 milliseconds as expected by the dashboard. Okay, so now we have the application code, and let's build a real ECU, so an electric controls unit. So that's the concrete component that we will put in the car. And for that, we use a Raspberry Pi with a few CAN bus modules. And we are packaging this using Nerves. So Nerves is an Elixir platform that will use build routes to create a very minimal Linux on which that will immediately boot on Erlang. And it will also use FWUp to update over the air or USB or directly on the SD card. That's a really nice project too. And So we package this, we put that in the car, connect it, and it works. We now have Thank you. So yeah, we now have that needle moving at the right to the right value when the leaf motor is running. Of course, that was just one little example, and we had to reverse engineer the speed, the handbrake, the throttle pedal, everything to have a running car. That's not the topic of today, but at least you have the idea. Again, it's not that complicated, and once you start working on this, you start worrying about the security of your car. Because you can see that it was not designed when the car was connected to the internet. So maybe things could be improved. Anyway, so that's it. If you want to know more about OVCS itself, my two colleagues are also presenting tomorrow afternoon, so don't hesitate to join them. Any questions?
Yeah, first of all, great talk. Thank you.
Thank you.
So when I'm teaching Elixir to people, one distinction or one example I usually use of soft real-time versus hard real-time is that you would not want to use Elixir for, say, example, driving a car. So I'm really curious about how you're approaching this and what sort of things you're actually using OVCS for in practice.
Yes, so it's not meant for a vehicle that would go on an open road. It's not yet certified. It's open source, but try it at your own risk. Then we have some parts today running on Arduinos written in C, like really to control the brakes or things like that. It might be a better idea indeed. But actually, for most of the cases, you anyway have delays, you have errors on the bus. So you have a lot of non-critical features on your car that actually can the soft real-time part is good enough, I would say. And then, in practice, we still have issues to work on. That's true. But we really wanted to see how far we could go with that Elixir stack. Thank you.
You said a process per emitted frame. Do you mean permitted frame type? Not for every single frame within your process. Is that how it works?
Per emitted frame, yeah. So you have the inverter status frame that is emitted every 10 milliseconds. So you have one process for that. But in Elixir or Erlang, the processes are really cheap. So you could have thousands of even millions of processes without any issues. It's really lighter than a kernel process.
Just a quick question about reverse engineering the CAN protocol. Is there some kind of community-driven effort to have, I'd say, most build-and models, a database a knowledge base of all these protocols and all these things? Because I did some kind of stuff like that on my BMW car because I had to fix the entertainment system. Yeah. But it's only on my blog. It's not somewhere it might be interesting to also have, as a side project, this kind of knowledge base built by the community.
Yeah. So you have some communities around specific cars, like the Nissan Leaf. You have entire forums about it. You also have Coma.ai that is providing an OpenDBC GitHub repository where they are trying to aggregate this reverse engineering. So yeah, it exists, but not for all cars, not for all generations.
Have you, besides reverse engineering the canvas, did you also consider replacing the RPM reader on the dashboard for one that's compatible with the Leaf?
Yeah, so that's the usual way when you convert to an EV. When you do retrofitting, most of the time people are just putting a new screen and it works, it's easier, but then it doesn't feel as seamless as it could. So in this case, we really reverse engineer the ignition lock as well so that it starts the electric engine and so on. So yeah, it's a taste, I would say. But it's really nice to see the old dashboard displaying the new value. Also, we didn't do it, but the goal is to display the battery level with the tank level needed.
So you mentioned during the talk and a few moments ago that you've got all these communities with all these DBC files for different cars and things, and then you're loading all these descriptions in YAML. So I was wondering, like, is there a converter, or why you're not just using the provided DBC?
I could show you an example, but the DBC file, it's a proprietary format and it's really ugly. But it's the default format, so I couldn't. Yeah, it was a sabbatical year where we did fun things, and I couldn't push myself in implementing this. But the idea would be to have like a conversion tool to go from the YAML to the, because here it's easy for anybody to read, and in the DBC file it's like impossible without a GUI that is really ugly too. So yeah, but I agree that it could be a good idea. We should support both, probably.
Yeah, thanks for the talk. Do you know if the OBD2 connector also exposes these CAN commands, so that you can reverse engineer it without like going to the motor and getting your CAN trace from where?
So the problem on the OBD, that's the socket you have in all cars to do the diagnostic. It exposes some things in a standard format, but you don't have access to all the values. So it's just like, yeah, the speed, the RPM, so you will probably have, but probably not at the same frequency. But you won't have access like to the handbrake state or the door state or things like that. So if you want to go as far as possible, you need to really reverse the proprietary frames.
So do you want to say that the CAN bus lines from the OBDB connector are different from the other? So there's a proxy or something in between?
Yeah, there is in most cases, so it depends. Like in the leaf, they expose in the ODB two lines for the internal one and also for the standard one. But on the VW, you just have a filtered version of the CAN.
Yes, one more question. Is there any way to use the Elixir code and run it on like ESP32 or the microcontroller platform instead of full-fledged Linux board?
There are some projects, but yeah, to run the beam, you normally need a Linux. But I think there are some boards that were designed to run Erlang on the metal itself. But yeah, we didn't try it. We also tried to use the cheapest board and easiest available, so we are using Raspberry Pis and Arduinos. But if you want to go further with that, you should definitely use something else.
It's called AtomVM.
Yeah, thank you.
Does the open vehicle control platform support automotive Ethernet and encrypted frames and these kinds of things?
Sorry?
The open vehicle control platform, does it support automotive Ethernet and encrypted frames?
No, not yet. It could easily be added, but no.
Okay, if we don't have one last question.
Just to follow up on what the person was asking here. What kind of ROM footprint does your Beam Elixir have? How much space does it occupy? You know, all the binaries and the interpreter and everything with the virtual machine. And also, what kind of memory requirement does it have?
I don't have the exact values, but it's really small. The footprint is really a few megabytes.
What about RAM?
A few megabytes too, but honestly, we should try. On a Raspberry Pi, you have much more.
Sure, I'm just interested in kind of having an embedded solution, eliminating memory fragmentation, which can be difficult because I assume these languages, they require, heap and use heap extensively. So.
Yeah, it's you need an OS and so on, so it's not.
Thank you.
Okay, thank you.